Bjorn is going to talk this evening. He's a graduate of Stellenbosch. He spent some time in the mining industry, and I can't emphasize how important time in the mining industry is to any geological academic. And then he's gone back to academia. He tells me that he's generating publications, which is obviously, just what universities do. Much more usefully, it's about the quality education of the next generation of African earth scientists. So Bjorn is going to talk about gold, and it's straight over to you, Bjorn.
Thanks, Gillian. Thanks very much for the introduction. And yeah, apologies to those in the audience here who perhaps didn't hear that as clearly, but I think by the end of today, you'll know who I am. So welcome. Thanks for hosting me. Thanks for hosting me online as well. It's going to be a little bit of a balancing act here in that I'm speaking to an online audience as well as to an in-person audience. So I hope it comes through clearly enough. And yeah, I hope I don't lose too much of the little bit of charisma that I do have through this intervention. But let's try it. I will be talking about gold in Africa, in Africa specifically. Can everyone see my screen? Yeah. Sorry, it's always a little bit of a balancing act here. Okay, right. And so I'm going to be using a pointer here and my hand waving for the audience here as well. So bear with me, let's see how it goes. This work isn't all my own work. A lot of this work is built on the work of my students. And as academics, what we do in our offices or our ivory towers is we sit there and we fill out forms. And then when we finish our forms, they give us more forms to fill in. And hopefully by the time we finish those forms, our students have written us some nice papers that we can just put our names on at the end. So this work is built on a bunch of work by my master's students, by several of my PhD students, and I've also drawn on some of the work of my colleague, Prof. Alex Kisters, who's a very efficient form filler outer, so he gets to do a bit of real science as well. So he's got some really nice work there with some of his students. This is the opening slide. I recently gave these series of talks or, iterations of these series of talks in Australia. And there I was trying to impress upon the Australian community that, we have a exceptional endowment of mineral resources in Africa. And that goes everything from sort of the world's biggest resource of platinum group elements in the Bushveld igneous complex, the supergiant copper cobalt mineralization, the Central African copper belt, world's largest bauxite deposits in Guinea, world's largest on-land phosphate deposits, manganese deposits, etc., etc. Another point that I raise, I think it's a very important point, particularly for the students and for those more interested in environmental geochemistry, is that because of historical mining and because of the mining that continues to happen, there is a inherent footprint. And so it becomes very important to also think about how we're going to mine in such a way that it's sustainable for the countryside and for the environment. So that's something, I try to imbue into the students. I tell them, you guys are the custodians of the earth resources. So let's think about this critically and make sure we do it in a sustainable manner. Okay, so just sort of building on that idea that we have all these world-class endowments, that this is a super rich continent, I think the next graph really speaks in contrast to that, right? There's a bit of antithesis, I guess is the word, or disconnect here, in that the amount of exploration spending in Africa is this little blue line at the bottom there. Okay, some years, very little exploration happening in Africa. And if we put that in context, if we look at the size of Australia in terms of its land surface area, or Canada in terms of its land surface area, Africa is a massive continent, yet we're spending much less in terms of exploration budget towards finding the future supplies of Earth's critical resources. So I think you can look at that from two different perspectives. Depends very much if you're a sort of glass half full type of person or a glass quite empty kind of person. So if you're a half empty, you'd probably say this is a failing, right? But what I like to tell the students is that this is an opportunity, right? It means there's probably a lot of undiscovered, louder, Okay, apologies. I have to talk louder. Okay. I see it as a very important opportunity for future generations of Earth scientists to go out and find new resources. I think there's vast tracts of underexplored land. I think there's a lot of new exploration paradigms that can be applied. And I think part of this whole program or the series of seminars focus largely on the bits, right, is also to think about the bits in non-standard or alternative paradigms, because that can raise the exploration opportunities and prospectivity. So, you know, and as much as there's opportunities for exploration, I think it is also not always easy. These are just some images that came from my very limited time in the exploration sector. We were looking for iron ore deposits in the Republic of Congo. And I think what the images indicate is that the working conditions can be quite tough, right? Lots of rainfall, muddy environments, lack of outcrop, limited infrastructure, and very remote. So this image on the whatever side that is, left or right, is taken from a cycle that we used to do on our days off on a Sunday. It's about 40 k's to the Gabon border, where we'd go looking for wild elephants. And this is the largest town that we'd pass through. We only passed through 3 towns, this one being the largest one, and that's looking from one side of the town right the way back to the other side of the town. So very, very remote, right? Okay, so it's exciting. I think there are lots of opportunities, and that's, I guess, take-home message number 1 for the students in the audience. You're not here, by the way. Okay. The second major concept that I'm going to try and get across through the duration of the seminar, using the backdrop of Africa's evolution, is how orogenic gold deposits form. And I find this image over here probably the best way to break down the formation of orogenic type or metamorphic mesothermal gold deposits into its most fundamental components. That being, what is the source of the fluid that transports the metals? What is the source of the metal that we're interested in this instance, gold? And importantly, what is the source of the ligand or complexing agent that serves to increase the solubility of gold in the solution and move it around through the system? The second component is the transport components, and these generally rely on some sort of tectonic events to ensure that you have the correct crustal architecture or fluid conduits through which the fluid can move, right? And so there's a driver for that fluid flow event. And then importantly, the trap site, right? And we need these trap sites to be close to surface or sufficiently close to surface that we can access it. And we need it to be sufficiently concentrated so that you get all that metal into a small enough area to give you a high grade deposit. Okay, so trapping mechanisms can be chemical, can be physical, physical or structural, or can just rely on enough or sufficient fluid focusing that you shove enough water through there that enough metal will ultimately drop out. Okay. Final thing sort of happens after the deposit has formed. These are later modifications. They can be from downward percolating rainwater, so what we term supergene events, and they can be related to subsequent deformation events or to remobilization events. And so I'll give you a couple examples of where we've seen some of these processes operating in the deposits we've looked at in Africa. Okay, so I'm using a sort of temporal framework here, working backwards in time. So, you know, not long after someone said, let there be light, you started to form these original Cratonic nuclei. So what are they? They're like the seeds of the continents, or seeds of what will ultimately become Cratons. And those Cratons ultimately amalgamate to form continents or even supercontinents. And some of these, sorry. Africa has some really old pieces of continental block, right? And just a couple of them are showcased here. I hope you guys are remembering all these big words because I'm going to test you on it afterwards, right? But up in the northeast of Congo, got the Bomu block, which be between 3.4 and 3.7 billion years old. Got Tokwe segments in Zimbabwe, also greater than 3.4 billion years old. And then in South Africa, we've got various of these greenstone belts, some of which represent the oldest and best preserved sequences of siliciclastic or sedimentary successions. Okay, that really makes South Africa remarkable, in that you've got these well-preserved sedimentary sequences in places like the Barberton Mountainland. So if you haven't been out there already, I think it's a very worthwhile trip from a geoheritage perspective to go see these rock formations, right? And why I say it's in contrast to those other old blocks that I've spoken about, most of those are high-grade metamorphic terrain, so you can't really see what was happening greater than 3 billion years ago. So anyways, the first deposit I'll talk about is from one of these greenstone segments. It's the Barberton Mountainland over here. There have been some very good talks on it already by some of my colleagues in the university. So I'm going to touch on it very briefly as the first example. One of the oldest and best preserved gold mineralizations in the world, with the gold mineralization anticipated to have taken place around 3 billion years ago. That sort of age is still a little bit debated. The host rocks are between 3.5 and 3.2 billion years, and they represent a succession of, basal, mafic, ultramafic rocks, the Overberg group, grading upwards into these siliciclastic sedimentary sequences of the fig tree and the Moody's group. Most of the mineralization, the well preserved or major endowments of the mineralization are sort of centered on this hinge zone over here. There's a zoom in over there. You can see the Fairview mine, the Sheba mine. And that arcuate shape is really a function of this fold and thrust belt that's sort of been refolded against these competent granitic flussons or batholiths on either side. So squeeze it all together, and that's been quite important for the overall gold mineralization. So this is some of the work by Caitlin Jones and Alex Kisters. I think it gives a good idea of the regional controls on fluid flow, and it again speaks to that refolding event that I've just spoken about, where the fluid then preferentially, or the gold-bearing fluid preferentially migrates into this hinge zone shown over here in the blue coloration. And there they posit that a lot of the fluid flow is happening just on grain boundaries along bedding planes and mobilizing into this hinge zone where you find most of your major deposits, okay? There are some other ones outside, and those are related more to sort of brittle deformation events in competent lithologies. So regional fluid flow into a hydraulic sink on the regional scale. On a more local scale, again, just highlighting the importance of fluid focusing. This is work by Jonathan Gloyn-Jones, and he looked at the main reef complex, which is on the Sheba faults, which is formed at the sort of intersection between these two synclines over here, the Eureka and the Ulindi synclines. And with the sort of textual movements or displacements along that fault, you get sort of opening up within these dilational jog sites. Again, that dilation becomes an area for preferential fluid flow, and more gold-bearing fluid that you shove through the system or through this dilational jog site, the more likely you are to have some of that gold just drop out on a function of its, drop in solubility and become mineralized. So that's a good example of, a local scale trap site. We've looked at it a little bit in our study group also from the geochemistry perspective. What we found in one of the early honors thesis by Lindo Makatini is that the gold is predominantly associated with this black quartz, which is an anomalous color. We've all seen white quartz in the Cape Fold belt here. We've seen pink quartz at the Scratch Patch, as rose quartz. But the black quartz is somewhat anomalous. And so we conducted some Raman spectroscopy, which showed up that there was disordered graphitic material within that quartz. So we took that further as part of our research, and we wanted to understand whether you could apply some of these metallurgical principles of using things like carbon and leach, carbon and pulp, where the disordered carbon or amorphous carbon is used to absorb gold and in that way increase the solubility of gold in the fluids moving through the systems. In that way, perhaps explain the anomalous endowments of gold in these greenstone belts. We didn't find that, but we did find some other very interesting textures, and this published last year, and I think it's probably the most spectacular image of gold that you're just about ever going to see, right? And so in this sort of gold grain here, which is viewed under the scanning electron microscope, that scale bar is 10 microns in length. You can see this little pocket of what must have been filled with some sort of fluid or geological medium, and within it, you've got all these tiny spheroidal gold particles. So remember, I spoke a little bit earlier about potentially just shoving a whole bunch of fluid through because of its low solubility limit. If you shove enough fluid through there, you can get a gold deposit. The other way of doing that would be, okay, if we can find a way of somehow raising the amount of gold in the fluid, then you don't need to shove as much fluid through. You can have less fluid, but also a high likelihood of gold. So this is a conversation that is actively happening. There's a lot of research going into the role of colloidal gold, so gold nanoparticles, gold colloids, moving around in the fluids and then ultimately coagulating in some manner to form larger gold grains. That's what we thought we were seeing here. We thought we were seeing some sort of Ostwald ripening process where the little small spheroids, in a viscous medium will preferentially dissolve to preferentially form the larger colloids and also the large gold grains with this protrusion going outwards into that medium. So it's an area of active research. I think it's very exciting. A lot of nice work coming out with the modern technologies. Okay. So moving a little bit forward in time, the purple colors just represent the growth of these cratons. Remember, they started as little nuclei. The gray hasn't yet existed, so it's still to come. But around this time, you're starting to get some form of stabilization on the Congo craton. Not sure what's happening in the center here because it's covered by a lot of sort of most recent cover, but they believe that there's old cratonic nuclei in there. In Zimbabwe Craton, you've got this typical dome and keel structure with greenstone belts and granite basements. And you can see in the Kibali Craton that the Kibali block and the Witwatersrand block have by now coalesced. And we have the development of this world-class Witwatersrand Basin. Okay, I'm not going to speak too much to the Witwatersrand Basin. I think the rest of the seminar series has dealt with that quite explicitly. And if you haven't seen the videos or the recordings of those talks by Neil Phillips and Julian Bjorn and the rest of the sort of lineup, I do urge you to go check out on YouTube the recordings and catch up. So anyways, talk about gold in Africa would not be complete with at least one or two cursory slides on this. So for those of you that are not familiar with the bits, it represents on the order of 1/3 of all the gold that has ever been mined going back in time. It is hosted in a sedimentary sequence of the age between 2.7, 2.9 billion years old. And from that sedimentary sequence, we've had on the order of 52,000 tons of gold being won. Okay. Importantly, there's debate that surrounds the formation of the bits. We've heard a little bit about that in the past weeks, but the debate swung between a placer model, hydrothermal model, a modified paleoplacer model, and recently a bit of work coming out where they predict that the gold is, or they suggest that the gold is coming out from river systems and being trapped on algal mats. So again, not going to get into those debates because of the time constraints here, but I will just leave you with two images of some of the samples that I have in my office. They're really exciting samples, but they look like two completely different gold deposits, right? This is a sort of gold-carbon association versus this one being the more classic conglomerate-hosted gold association. And I think I'm excited about where the rest of the seminar series is going to go with some of the active debates that are going to happen in the two forthcoming or the two additional sessions. And I think it's worth everyone who's interested in the bits joining in those sessions, joining in that debate, and hopefully we can, after 100 and so years, get to the bottom of how this deposit formed. Okay. Also, the Mesoarchean, I'd mentioned that the Zimbabwe Craton had formed by that stage. I haven't done much work there on gold in Zimbabwe. So this is relying on work by Bob Foster. He's done a lot of work in Zimbabwe. And they sort of summarize the distribution of all the gold deposits given by these orange dots over here and the size, the relative size. So they got some world-class deposits there, or some really, good deposits greater than 4 million tons or more, sorry, 4 million ounces. And as many as 650 different occurrences or deposits. I think, again, the sort of political framework in Zimbabwe and the state of that state for the last 20 or 30 years means that exploration hasn't focused as actively as it could have in this country. And I think there's a lot of potential out there for discovery of new deposits, or at least expansion on the resource base of those that are already discovered. Importantly, and I'll come back to this when I also speak about the Tanzanian goldfields or the Lake Victoria goldfields, most of these deposits are again hosted in these slivers of Archean greenstone belt material. And so again, I think it was Tom Blenkinsop's work, looked at the distribution of the gold deposits and found that most of them are associated with greenstone fragments, except about 24%, which sits within granitic rocks. Right, but of those granitic rocks occurrences, 96% of those occurrences were within 2 kilometers of a greenstone belt, or within the sort of vestiges of greenstone float inside the granitic blocks. So I think it's an important part of the story, which we still need to get on top of. Okay, moving forward in time, and this is now into the near Archean. Not everyone's familiar with these terms. What I have got on the bottom over here is a sort of temporal scale to help me along. I always get confused with all the different names. So you can also follow the temporal scale at the bottom there. But in terms of Africa's evolution, we've had a collision between the Uganda block and the Congo Craton, giving rise to this West Nile belt over here. The Tanzanian Craton has also started to develop its own greenstone belt fragments, which are, I think needs some work, and I'll be involved in an initiative that relooks at the East African exploration, particularly how these greenstone belts relate to one another. And on the Kalahari Craton, we've had a collision between the Zimbabwe Craton and the Karpal Craton, giving rise to the Limpopo belts. And there's some mineralization, some gold mineralization there. The Renko deposits are well known, sort of higher grade, so high metamorphic grade deposits, which I won't speak about at this time. Okay, so I will talk about deposits up on the Congo Craton. This is some of the recent research from one of my PhD students who graduated last year, Dr. Jan Parker. And he did some very nice research looking at what is one of the world's top 10 biggest gold producers. That's the Kibali Gold District, currently being operated by Barrick Gold. Okay. Kibali main deposit, the KCD deposit, sits down here, just offset from this major lineament or suture zone known as the KZ trend. Okay, what you'll notice also is that most of the other satellite deposits in the area are distributed along the KZ trend. And for me, that implies that the main fluid introduction event has taken place along that major structural break. Okay, this one's offset. And again, this is a stack, fold and thrust belt. And so you move, you've got additional structures that are sort of semi-parallel to that main trend. But as you'll see as I walk through these slides, there has been a significant deformation that has controlled the final architecture of the deposit that is formed there. Okay, the last thing I want to bring your attention to on this slide is just the prevalence of these folded banded iron formation sequences. And I'll talk about the importance of banded iron formations as a chemical trapping mechanism that gets gold out of the fluid phase and into the solid phase. Okay. So this is just an example of that sulfidation process is happening. The chemistry that underpins that process is really, you've got an iron oxide in the form of magnetite, with Fe2+ and some Fe3+ in the structure. And you've got gold in solution being transported by the bisulfide complex, such as HS-, right? Two of those. So that is the complexing ligand that helps to increase the solubility of gold in solution. But when that that gold bisulfide complex comes into contact with these magnetite mineral particles, the sulfur will go from the gold complex and change the magnetite into pyrite. All right. And in doing so, there's nothing left to complex the gold, so the gold has to drop out. And that forms a chemical trapping mechanism for the gold in solution. We can see that process taking place here. Unfortunately, it's a little bit sort of small, but you can see what was once a magnetite crystal over there has been sulfidized to form pyrite. There's still some magnetite, hasn't yet been completely replaced. And associated with all of this are these gold grains. On the sort of larger coarse scale, you can also see the remnant magnetite bands. They've gone to this pinkish color, which is siderite, that's an iron carbonate, and then ultimately to pyrite, right, which just represents the dropping out of the bisulfide complex to leave behind gold and pyrite. And you can see the grades there, relatively high grade, right, 28 grams per ton. Okay, distribution of the deposits track these banded iron formations, or what once was banded iron formation, are being pervasively altered to a carbonate sericite sulfide lithology. And I'll talk a little bit more about the distribution of the ore bodies as a function of the subsequent deformations. You can really see how those layers have been, folded and bent together. Right, and this is just looking at from one plane. If you look at it from the other plane, it's also being squeezed together like that as well. Okay, it's going to be sort of nodular, not nodular, sort of concentrated gold loads. Okay, a little bit of complex slides, get that idea across. I mean, if you had enough time, you could sort of try and understand the evolution of this belt, but really, if you look at it from the northwest, it first became a northeast foraging fold and fast belt. And if we sort of cut this and look at it from the opposite direction, it got refolded in the other orientation. So it gives sort of a fold it, and then fold it again becomes these cuffs, right? And so what we predict happened here is that the gold came in quite early in the belt, following that KZ trend and parallel sort of structures. But then because of the subsequent deformation, that gold has been squeezed out into the fold hinges, but those fold hinges are in two orientations. They almost become these like sheath type folds where the gold concentrates. The other thing that happens is you have the development of these high strain zones that truncates the gold globes, right? And what I like about this image over here, which has sort of been digitized by Jan, is that it tracks what you see on the macro scale, or on the sort of regional scale, is the same as what you see on the sort of small coarse scale. That's something I try to also imbue in my students. What you see on the small scale is the same as what you see on the big scale. So here you can see the folding of the magnetite layers. You can see how they've been cut by these high strain zones, and you can see the sulfidation process taking place. And we think that the gold localization has been strongly controlled by this deformation history, and that some of the upgrade has taken place on account of sort of fluid-assisted mass transport into fold hinges. The next deposit I talk about, just briefly, I haven't worked here, is the Lake Victoria goldfields there in Tanzania. But what I highlight here again is that most of the deposits are hosted within these greenstone fragments. So I think that's again very important. The absolute host rock varies from sort of granitic bodies to metasediments to metavolcanic rocks, but it is a world-class gold district, and a lot of exploration still happening in the Lake Victoria goldfields. I think there'll be some exciting findings coming out of there. Okay, we're still all right with time, Henny.
Half an hour.
Okay, no one's fallen asleep yet, so I'm doing something right. Okay, so we're moving forward in time a bit now. It's sitting about 2 billion years ago, 2 billion years ago, right? What's termed the early Proterozoic. Tectonics happening at this time, generally a bunch of sort of deformation, accretion happening at the edges of the Congo Shield. We've had the Tanzania Craton collide with the Uganda block of the Congo Shield, potentially also other parts over here, and that's given rise to this Rwenzori belt. Mention the Bangweulu block. It's an exotic block at this stage. I'm not sure where it goes to. I think it comes in and causes a bit of mischief in the middle here, and we'll talk about that as I speak about two of the other deposits that I've spoken about. So moving forward, again, a lot of developments on the Congo Shield, the Usagara belt, the Ubendian belt, forming a collision between that Bangweulu block and the main Craton. and a bit of stuff happening here on the Carpal crust. I'm not going to go into too much detail, not too important for gold mineralization at this place. So we're going to focus here on the Ubendian belt, where that Bangweli block has just sort of docked on. And what's interesting about this belt is that it's been activated and reactivated multiple times. So I think that Bangweli block has come in, it's moved apart, it's a rifting event. They found some sort of new oceanic crusts in this area. It's docked on again. And if you look at the sort of distribution of the current East African rift and some of the lakes in the area, it looks like it's spreading apart again. So you're reutilizing the edges of these Cratonic blocks multiple times through the various sort of major tectonic cycles. That's sort of tracked in the distribution of the gold deposits in the Ubendian belt. We've got the Alupa goldfields, which are on the order of 1.8 billion years old. We've got the Simpanda goldfields up here, which is on the order of 1.1 billion years old. And then you've got several Pan-African sort of 500 to 600 million year old deposits further south. And that just relates to each time the Bangweli blocks open up, come back in, opened up, come back in. Okay. Alupa block is sort of preserved a bit of a graben structure. Again, I haven't worked there, but it's hosted by sort of 2.7 billion year old foliated granites and the unfoliated intrusives, which may be related to the same tectonic event that brought the gold, and that was about 1.9 to 1.8. Mineralization, native gold with some anomalous sort of tellurides and base metal sulfides, and associated with the base metals particularly are the sort of more saline fluids that might have been responsible for that mineralization event. And I'll come back to this again later on, where I explain the importance of salinity in terms of mobilizing base metals plus gold versus just that bisulfide complex, which mobilizes just gold. That's, I think, something that Neil's spoken about before as well. Okay. During the Mesoproterozoic, not too much going on here. Karanga and Kola belts depositing. You've got stuff happening at the south of Malawi, the Eremite belt, which I'll come back to later on. Within the African or the Kalahari Craton, this is where we have the major formation of the Namakwa-Natal province, which is from accretionary tectonics and, certainly the Natal belt, sort of docking on an abduction of some ocean crust and exotic terrains. Also in the Neoproterozoic, we've got the formation of the Katanga supergroup, Mozambique belt, a series of these extensional basins. The Katanga supergroup, with its subsequent deformation during collision between these two blocks, gives rise to at least some of the copper mineralization that we see in this world-class Central African copper belts. So again, the Central African copper belt, really important for both copper and cobalt being one of these battery metals that we're all very interested in. But all of that is associated with active salt tectonics and a lot of salinity in the fluids, and the salinity is able to mobilize things like copper. So at the moment, we'll be going back and looking at the West Congo belt with similar types of mineralization, because we know that we've got Central Africa copper belt, Kalahari copper belt, and even in the sort of north of Namibia, we have some copper mineralization might be related to this sort of contemporaneous events. So, okay. And then the sort of most recent major collision that's taken place is between the Kalahari Craton, the Congo Craton, and then even above that, the Saharan Shield, to give a series of what we term these Pan-African mobile belts. Okay, a lot of that deformation, again, deformation being really important for driving fluid flow and for creating the crustal architecture for the fluids to move through and give rise to ore deposits. So I'll talk about just one or two examples from there to, again, illustrate some of the processes that take place in forming gold deposits. So I don't think we'll get to the Damara belt, but I'll talk about a small occurrence in the South Eremite belt, as well as coming back to this Ubendian belt, where we did some nice work on a gold occurrence there. Okay. Sorry. So this is the Amani area, which is, if I go back a couple of slides, just here at the bottom of your Tanzania, close to Lake Malawi, in the Livingstone Mountains. Sorry. And we went in there, sort of like a gold occurrence, hasn't been mined yet. There's an Australian company looking at it in some more detail. But we were able to sort of unravel the geology using modern geochronology techniques and by using field mapping techniques to disentangle the fact that there's a carbonate sequence overlain by a siliciclastic sequence deposited from around 700 or 800 million years ago. And then all of that has been deformed during the Pan-African orogeny of 500 to 600 million years ago. Okay, the area has also got some basement gneisses. The basement rocks have seen a much more protracted geological history. Again, speaking to that Van Guilub rock coming in, coming out again. So it's seen the 2.1 to 1.8 billion year old Ubendian orogeny, the around 1 billion year old Kibaran or Uramine events, and then these Pan-African events over here as well. We were able to use fluid inclusion microthermometry. That's where you sort of take a piece of the quartz material and you polish it really thin, and you look for these little pockets of fluid that were trapped as the quartz was growing. That tells you a little bit about the fluid that was responsible for that rock type or for that mass. And what you can see within this fluid inclusion, so this is a 20 micron diameter, 20 thousandths of a millimeter. You can see that there's CO2, there's water, and there's a cubic halite crystal, which implies quite a lot of salinity moving around in these 700 million year old sediments. So again, we draw some correlation there to the Central African copper belt, to what we're seeing in the West Congo belt as well, and potentially extending on the area that might have been affected by, highly saline fluids giving rise to mineralization. The salinity, I said I'd come back to it, plays an important role because whereas gold is mobilized by the bisulfide complex and under oxidizing conditions and acidic conditions can also be mobilized by the chloride complex, base metals like copper, zinc, and lead rely on chloride to move them around. So we'll see that at this deposit, it's not just gold that we find, but also gold and copper. Okay, so here's some of that copper chalcopyrite given by the sort of goldish color over there. It's starting to alter to covalite, which is a supergene product of the copper as it sort of the chalcopyrite as it starts its breakdown. And if that breakdown continues by seeing more and more rainwater moving through the system, it's going to strip all the copper out of the system and you get left behind with just iron oxides, which is what we term a gossan. Okay, gossan is very important exploration markers. It means that you once had sulfides there in the area. So these were sulfides that then got oxidized to form oxides because of the oxygen in the rainwater, and it gives you this characteristic sort of boxwork texture, very brown, gossanous material. I always tell my students that they find some, they don't tell anyone, they phone me straight away. Okay, they haven't phoned me yet. Yeah. But anyways, associated with the gossan is a lot of the gold. And so we looked at this from a sort of microanalytical techniques, and under the scanning electron microscope, we actually noticed that some of the gold migrated preferentially along those boxwork channels. And so what we think is happening here is that the gold is actively cycling in the low temperature biogeochemical environments and mobilizing to form a secondary gold. You can see that in the gold chemistry signatures over here, where the yellow line gives the gold concentration of the original gold. But if you measure the gold in these little rims, it's much richer. So it's lost a lot of its silver depletion given by these lines over here, and the gold's gone up to sort of a 97% purity. Okay, so that's one part of the story there. The other part of the story was looking at the gold that then was liberated and mobilized into the sort of conglomeratic fluvial channels. And again, we saw some very interesting textures there. We saw very fine overgrowths of this secondary gold, again, having a much richer gold concentration. So this is, on this axis is the silver. So if the silver's dropped right off in the rim, it means that the corresponding gold fineness is much higher. You can see on the sort of false color map here again, it's quite a lot of silver, less gold or less concentration gold in the core. But as you move into the rim, that silver drops right out, and it's mostly just pure gold, basically. Also found nice spheroidal nanogold particles floating around these sort of river samples. And we interpreted all of this to suggest that you have secondary gold growth as part of this active biogeochemical cycle in that sort of buried river channel. So Dave Gore gave an alternate explanation for these gold-rich rims based on recrystallization because of mechanochemistry. I think it's a very, very elegant explanation, but you know, we had a slightly different take on things. So this is just the overview model. You have the orogenic gold form with some copper. It gets weathered into the river channels and then gets buried as you have sort of continued rifting in the area. So those early river channels are buried under more recent river channels. And what we see in the river profile is that the redox conditions within that sediment profile fluctuates. You can see that in the mottling of the iron oxides, giving sort of reddish colors mottled with gray colors, which implies redox shifts. And if we think about the chemistry of gold under fluctuating redox conditions, we can see that become more or less mobile. So either dissolving and recrystallizing to give the secondary gold overgrowths, nanoparticles, and what we see. And I think this is something that's quite well established, that it is active in biogeochemical cycles, biogeochemical systems. Good example being those massive nuggets that were found in Australia, the Welcome Strange and the Welcome Nugget, which again, if I tell my students, they find something like that, they must phone me straight away. Okay, I'm just going to talk about one last deposit in Malawi. Very small scale, I wouldn't call it a deposit, more of an occurrence. It's in the sort of southern Eremite belt. And the field area that my first PhD student worked on is shown by the map over here. Most of the rocks in the area, quite high-grade gneisses. And I'll just zoom in here. So all the sort of, okay, let me go run back. So we interpreted what we're looking at over here to be one of these sort of fences. So you've had a thrust event, and then it's sort of eroded or weathered through that thrust to leave a window, so you can look down into what was below the thrust sheets, if that makes sense. Okay. So in the hanging wall of the thrust, you've got higher grade gneissic rocks with some very old ages associated with them. Whereas in the window, what we're looking in the footwall, there we find sort of a lot more pegmatites, mineralized sort of pegmatite formation. We find only one age distribution. We only see these 600 million year ages. And the rocks themselves aren't gneisses, but rather more like schists. So I think we're quite confident in that interpretation. Importantly, the Mozambique orogeny that gives rise to that thrusting was a long-lived orogeny. So the deformation that happened subsequently might have formed originally a gold deposit that was then subsequently deformed. We saw that on the sort of microtextural scale. You see a sort of smearing out of the sulfides. This is X-ray computed tomography at the bottom here. It's not very clear. But you can see how these sulfides have been smeared out. You can see in the pyrrhotite lenses, they've sort of been smeared out as well. And if we look at the gold distribution along this river valley, it's distributed for 16 kilometers in length. So it's not one well-defined deposit, but what might have been once a well-defined deposit has since subsequently been smeared out. And so we haven't been able to find deposit there, but much of the sort of upgrade that does happen now then happens in the river systems by sedimentary processes. So that's what the artisanal guys in the areas are getting out. And I think, you know, there's similar analogies in places like Klondike and Nome where there isn't a well-known hinterland gold source. Rather, the concentration is more effectively conducted by the sedimentary processes. Okay, so I'm not going to run through all the recent events, but I'll just leave you with a sort of overview slide of where all the gold deposits are located on the African continents. What we've seen as we walk through it, there's obviously lots associated with the Wits, but then for the most part, many of the other deposits associated with these greenstone fragments with, you know, smaller occurrences known in the more recent mobile belts. And I think that's where a lot of the exploration paradigm needs to move to the sort of more recent mobile belts. Okay, so just to wrap up and to bring it all together, it's perhaps a bit of a sort of overview of how orogenic gold deposits form based on what some of the things I've spoken about. The first is we spoke about source, right? And the source of the fluids is typically for these types of deposits metamorphic devolatilization reactions. As the metamorphic grade increases, as the pressure and temperature increase, so the hydrous minerals break down and release fluid that is able to move through the system and mobilize gold. Typically happens at the green schist to amphibolite facies. And there is an important control bicarbonate chemistry to ensure that the pH is optimized towards mobilizing gold deposits. Okay, the source of the metals, here I rely quite extensively on Ian Pitcairn's work, but he's looked with high resolution chemical assaying techniques at the distribution of gold through different metamorphic facies, and has shown that you can dehydrate metavolcanics, metabasaltic rocks, metasedimentary rocks, and all of that would provide sufficient metal for forming an ore deposit. Okay, and then the source of the ligands, this is predominantly for these gold-only deposits through the pyrrhotite to pyrite conversion that happens as a function of increased pressure temperature. But if there is salinity in the system, you will give rise to deposits that have not just gold, but gold plus base metals like the chalcopyrite that we saw. Okay, and just, related to this concept of the source, we can think about the role of nanoparticles and colloids going forward as well. In terms of the transport, again, we rely on a scaled approach when we think about the transport. So it can happen at a regional scale or at a local scale. And the important thing is that you focus fluids through the right types of structures, such that you can localize gold into ore shoots. Importantly, if there's a rheologic contrast between different rock types, that forms preferential siting of fault networks often, and this sort of thing that Alex works on. And one of the points I leave off with here, and maybe it's because we're asked to leave with sort of contentious type issues, is, why is there so much more gold associated with those Archean greenstone fragments versus the younger mobile belts? And does that speak to secular or temporal changes in the fluid chemistry, or related to secular or temporal changes in the tectonics? And there's this debate about horizontal versus vertical tectonic sort of processes. Certainly the rocks that I've seen in Barberton at 3 billion years old, that deformation, that all look like lateral tectonics. But I guess the debate's still open. And finally, just the trapping mechanism, second to final, just the trapping mechanisms. I've showed you examples from the Kibali gold district of how the banded iron formations control the distribution of gold on the regional scale, but then also on the local scale, how that sulfidation reaction is responsible for dropping the gold out. There are also physical trapping mechanisms. So with each earthquake or slip event or rupture events, you get rise to fluid pressure fluctuations. I didn't speak about that at all today, but it is also a very important mechanism for dropping the gold solubility. And the final point is, if you can just localize enough fluid, and just with a decrease of solubility with temperature, you should be able to form a deposit that way as well. Okay, and then finally, modification. I think I've shown quite nicely how the gold does mobilize and move around in a low temperature environment. We saw that the redox fluctuations might be important towards exacerbating or sort of enhancing that effect. And we can see how sort of gold moves in the Gaussian environment and can upgrade in terms of its fineness. So I think we're quite lucky to work on that field site because many of the near surface gold deposits have already been found and mined out. So if you look at old historical records for places like Barberton, the gold was richest in the near surface environments. I think it's because of this the supergene effect. They talk about forget the name now of that main quarry. But anyways, the gold was so rich that it used to clog the stump mills, right? I think part of that is just, I've got some sample that material. It's all Gaussian. It's all seen the supergene upgrade. And then finally, this idea that deformation can have dual effects, right? It can either sort of localize gold into the secondary and tertiary fold hinges, as we saw in the Kibali area, or as we saw in the Eremide field site, the deformation seems to have smeared out the gold, and it leads to a downgrade in the gold grade. Okay, so with that, I think it was a bit of a whistle-stop tour of how Africa pieced itself together. It's also a whistle-stop tour in terms of how orogenic gold deposits form. But I'm very hopeful that you took something from it and you enjoyed today's presentation. So thank you.
Bjorn, thanks very much, and you very successfully kept on time.
Thank you.
I'd just like to observe that you've actually made a really big leap in that your box is not a box of fluid that then went somewhere else and picked up the metal, that then went somewhere else and found a nice place to go and sit. But in fact, your box is of fluid and metal together, and that process is so much more efficient. So that diagram that you had of a big box and source and a small box of sink, and also one with enormous lateral motion, you had it left to right rather than up down. I thought was really, really interesting.
Thanks, Julia.
Okay.
Can I be an absolute pain, because you had a fantastic and the slide became more and more fantastic as you moved away from it and the further you got away from it. But could you go back to your slide that says gold in the Witwatersrand? Is that technically possible?
It is technically possible.
It's the one with gold in presumably the carbon leader.
This one.
Yes. So with that, I guess you guys can't see my mouse, can you? But with the so figure A,
Mhm.
and then in the middle of figure A, and then the bottom left, there is a fracture that goes across that bottom corner from 10 o'clock to 4 o'clock.
Like that.
And the gold on either side, presumably the yellow is gold.
Yeah.
The gold on either side of that fracture is completely different. And the only way you can have that is if the fracture was there before the gold came in.
Okay. So I'll have to go back and look at that sample in a bit more detail. I know one of my colleagues, Prof. Rosendahl, has run this sample through X-ray computed tomography and shows the columnar distribution of the gold in association with the carbon. I think it's the most fascinating gold sample after that spheroidal gold sample. But, I've seen nothing like it anywhere else in the world. So I think we truly are dealing with something unique here.
Yeah, I mean, I see Neil has been converted, and he's using the word of the moment, which is Perkins discontinuities, and the thoughts are that I mean, a lot of people think that gold comes in on fractures, and yes, it does, but it doesn't necessarily come in on a fracture you can see, and it often stops at these fractures. And these fractures are the barriers to permeability rather than the channels.
Okay, and can I just step in there, Julian? We've also got an audience here in front of us, so we need to just accommodate them a little. But fortunately,
Yep,
we
no worries.
don't have a general sound point. But maybe
Okay.
Bjorn can just hang on. Bjorn can just comment on the question that you've just asked and his response.
So I don't think there was a question there, but just for the audience that was speaking about these the gold distribution here along this structure.
He's talking about this.
And I think, what you mentioned at the end about fractures not just being a source of the fluid or a conduit for the fluid, but if the chemistry has changed sufficiently along those fracture sets or unconformity surfaces, it can form a warrior, and you can get fluid pooling beneath them. I think that's a model that's applied quite effectively for some of the uranium in Namibia, if I remember correctly. So yeah, I think there's definitely some value to your comment. Thanks, Julian.
Can I come in there? Next
Sure.
week in my talk, I'll present one or two slides, which remember my work was done 20 years ago, and we were doing this stuff and we never published it. But I'm going to present some slides where looking under with cathodoluminescence inside the carbon seam, where we see the most remarkable effects of fractures. And I think what Julian is talking about there may be very valid, but I also want some other things where those fractures are actually where the gold goes down. And I've got beautiful examples of it. So these fractures are actually, I'm glad Julian brought them up, are extremely interesting.
Okay, all right. Just a thought for me, and we've got some interesting people in here, including people like Adrian Reynolds, who's worked in the Birimian. We've heard a great deal about the Wits, and now today, courtesy of Bjorn, Africa from sort of Central Africa south. Would you like, Adrian, just to comment on the Birimian gold and the Ashanti Empire, and then the Malian Empire, and the amount of gold mined in North and West Africa?
John, I don't have any numbers.
Yeah, but just as a comment. Yeah.
But I mean, it's enormous. It is the biggest producer of gold in the world at the moment, West African Craton.
Come and talk here, please. Yeah.
Well, that's what I'm saying.
No, that's fine. Just give us your comments. It's one we've avoided so far.
Don't we ever raise hand after that, okay?
Okay, yeah.
Yeah, I mean, I was just saying that the Birimian of West Africa at the moment is the biggest gold producing area in the world, I understand. And I think we all more or less dismissed it for years because we saw it just as, well, it's just Ashanti, that's all there is to it. And you look at it now, it's a serious contender, and big deposits and big producers and so on. But John, I'm going to digress a bit.
Yeah.
The thing that Bjorn wouldn't talk about any further was the gap in ages where we get no gold, which to me is very interesting. And we know about it. We've talked about it. It's in the Archean. It's in the upper Proterozoic. The lower Proterozoic, and then you lose most of your gold. Every now and again it pops up. And then you've got the more recent stuff, the last few 100 million years. And is that because we don't explore where we don't expect to get it? Or is it just that that's where the gold is?
Good point.
Only question I'll leave with you with.
Okay.
And
Henny, you want?
Terence McCarthy has his hand up.
Terence McCarthy, speak up, just unmute yourself. Terence, you just want to speak to us?
There, can you hear me?
There
You got
it
me?
is.
Hello?
Yes,
Speak up.
Crossed my mind. Oh, is there any plan, or has it already been done, systematic dating of these various gold deposits using rhenium osmium? Has that been done?
Systematic dating.
Yeah. So what I presented is probably so there's a bit of feedback. What I presented is probably the start of where I'd like to go with this work, is to consolidate and systematically document all of the deposits in southern and central Africa on these two cratons. I think it gives a nice sort of overview of, at least one or two of these iterations of the Wilson cycle. So I think by looking at it from a meta-analysis perspective might be quite revealing. So part of that compilation which has started has included the available dates for gold deposits. And I know Mike DeWitt also started along these lines in the 90s. He had a nice big data set available to him, which I haven't explored yet. In terms of the use of rhenium osmium dating, it has its caveats, especially as you go further back in time. I think it has about a 10 or 15% error margin on it. So you're looking at a 3 billion year old deposit plus or minus 300 million years. It becomes a little bit difficult to take anything meaningful out of that. So I think that's part of the reason why Barberton mineralization has been so difficult to date. So yeah, I think as that work develops, I'll happily share it.
Neil Phillips has a text that says Perkins discontinuity with a question mark in the carbon leader. Maybe just he wants to, anything why he's asking that question, or will you tell us, Neil?
That's actually been answered by Julian already, and it was just something I learned from the talk 2 weeks ago, and I put in there because that's what it looked like to me. So it's been answered. Thank you.
Yeah.
Could I come back on the geochronology? Because about 5-6 years ago, I having sort of stopped in industry and gone back to think about things academic, got very upset about the geochronology that had been done in the Murchison Belt in South Africa. And I went to Neil McNaughton and got Neil to look at things and advise me. Now, Neil's the guy who sorted out the geochronology through the stratigraphy in Kalgoorlie. And Neil said to me, do not go out there and try and date the mineralization. You're on a hiding to nothing. Go out and date the rocks that cut each other. So every time you've got a field relationship that works, date the younger one and say, well, the older rock has to be older than that. And it was about building up a geochronology rather than just dating the mineral that you believe is somehow associated with the ores. Now, I'm not a geochronologist. I just listen to them.
Sure. Look, I think that's a very fair approach. Like I mentioned, there's definitely caveats associated with each of the geochron systems just about. So certainly the rhenium osmium one, which would be the one that you apply directly to the mineralization. I've mentioned, the error, but also the price tag, right? You're looking at about 50 to 60,000 Rand per age date that you generate, potentially with those massive error bars. And there's only, 2 or 3 labs in the world that can do it. So yeah, alternate approaches from field relationships, I strongly support that. The alteration assemblages, if you've got large enough micas, you can do things like argon dating, but it's also, got some limitations.
I think we should encourage others to cut in. Do we have a mine geologist somewhere in the audience who wants to say something?
Well, maybe you got to get Adrian back, who's been very strong.
He's not going to come again.
Mine geologist.
Spin my computer up.
Yeah. Okay, look. Anyone else, Eddie?
What's the question?
No, anyone else to contribute? I mean, the mine geologists, we've obviously got Keith coming up next week, Keith Kenyon. And then we've got 2 more follow-up presentations the following week. And maybe we can make sure we do have a mine geologist or 2 who can also contribute.
The Grant will also speak. And he was a mine geologist.
Yeah.
We'll come up on the talks as well.
Okay, but anyway, I think again another excellent presentation, and so I'm going to chip in here, Julian, and just say thanks to Bjorn on behalf of both the online and the in the hall group of people who've again found this all rather interesting. And importantly for me, it's great to see a young person compared to many of us, both sitting in the hall and online, and with your students.